All right, good afternoon, everyone. I'm not sure if I should start, but nobody from the Wharton team is here to tell me not to, right? All right, so I'm Hemant, Bhargava, and I'm presenting this paper with two of my colleagues, one of whom is here, Elizabeth, and Jan couldn't make it here. And this paper is really about labeling of unstructured text and producing good structured text, right? And this is work we did in the last year. It's sort of still ongoing in terms of thinking, but we have some ideas that I think they're worth sharing, so that's what I'm going to do here. All right, so labeling and AI, right? They're sort of joined at the hip, right? A lot of machine learning and AI depends on labeling. But also, if you look at what has happened in the last few years with generative AI and so forth, we now have machines doing the labeling as well, to do more labeling or to enable more AI, right? And that is often driven by cost considerations because, having humans to do labeling at very large scale, takes a long time and it's expensive. And at the same time, people have been trying to use generative AI LLMs for many different tasks, including different types of labeling and classification tasks. And they seem to be doing pretty well, right? But most of the time when we do this, our goal is something else, the research, or if you're a practitioner, your goal is to, solve some problems. And so you build your labeling enterprise sort of in a quick and dirty way, right? And we kind of started doing that on a project, and then we realized that there may be some value in understanding how best to use AI to do labeling. And can we produce some guidelines that would be useful for practitioners who want to get through the labeling task quickly, right? But still be, useful guidelines for them. So that's the question, what's your right design philosophy if you're doing labeling with LLMs?
Full screen.
All right, thank you. Wonderful. Right now, so that's the sort of basic question. How can we use AI to take complex text or later on other types of content and produce good structured content out of it? How we came upon this problem was that we were looking at these questions around corporate acquisitions, how acquisitions related to tech dominance, how companies get really big and dominant in the tech industry, and how that was driven through corporate acquisitions. And of course, to answer that question, you need a lot of data about acquisitions, who acquired whom, but what happened to the companies or products that were acquired. Did they survive? Were they killed? Did you acquire competitors? Those sorts of things. And in order to get that scale of data, you need some other data, which is often present in unstructured formats, including in our case, it was a corpus of about 27 million press releases collected from LexisNexis, right? And so there you have a lot of information about what's happening in business, including some of those stories relating to acquisitions and many others not relating to acquisitions, right? So the question was how to take this mass collection, identify the ones that pertain to acquisitions in technology industries, and then discover and understand what's going on with them. And the headlines are, you might think this is straightforward to look at a headline and determine that this is about a corporate acquisition. And turned out, and I'm not going to talk about that too much, but it turned out to be a very complicated task, right? So we then actually, for a while, we used human subjects, undergraduate students, to do some, labeling to produce training data for our ML tools. And eventually, we, timing happened to put us right into when ChatGPT was released. And then we started doing what turned out to be a series of experiments in using LLMs to do labeling. And what we learned from that is what I'm going to talk about here. And just to relate this to some of the things you've heard about today, right? I mean, in the first session with Eric, someone asked about, we seem to have exhausted all the data for LLMs. And I think what Eric said, and I totally agree with that, is that we are nowhere near that. There's tons of data that even the large, foundation models have not yet touched. But then if you think of all the data lying inside government departments and agencies, health, healthcare companies, education, right? There's so much content that people will, over time, as they want to use AI, want to go into the data, whether it's fine-tuning or something else, right? And then take the data and produce things that they can feed into machines to, right, for their tasks. So I think there's a lot of this that will be happening, and the idea was to see if we can produce these guidelines. So what I'm going to do is talk about how we did it, what we did, what we found, what were some of the basic discoveries, and then how do we convert that into a proposal or a set of guidelines for other people who might want to do this kind of labeling. Okay? All right, so, first of all, we kind of formulated the question of how to use AI to label unstructured text in a sort of more formalized way. And I think it's very evident to anyone that as you start doing this and look at the different ways you can use LLMs to solve a problem, including labeling, there's going to be a trade-off between how well it performs, what we'll call accuracy, and the cost of doing so, right? And so our idea in sort of refining the research question was to look at alternative designs or configurations of using LLMs and evaluate them in this accuracy cost trade-off. And obviously, higher cost most of the time will create higher accuracy. If it doesn't, that's actually a waste, obviously. But in some sense, you're looking for an efficient frontier among all the choices for how to do this. And if you look at, we've done labeling for a long time, like I said, with humans. And in the past, the chase for accuracy is really driven by the quality of the labelers, right? The human subjects you might recruit, how much education they have, what experience they have, what background they come from, and so forth. And yet, in almost any labeling task, you have a sense that the labeler is never perfect, right? Because these are complex content you're giving to them. And so it's very common in human labeling to use redundancy, meaning give the same task to multiple individuals, and then have some decision rule for which answer among different answers to accept. And sort of the most extreme would be that you repeat it, and if you get unanimity, you take the answer as being correct. And if you don't pass the decision criteria, then you have an unresolved task. And so one of the things we realize is that there is a trade-off between accuracy and unresolved tasks. The more you want to get high-quality responses, you will be left with many tasks that are indeterminate. All right. So in this, guidelines, I'm going to talk about 4 dimensions. One is which version, or more generally, what LLM do you want to use, right? How do you want to instruct the LLM? In our case, it's the level of detail in the instructions you provide. And then going back to this point about redundancy, to see whether the learning from human labeling of redundancy, how does that translate over to LLMs, to machines, right? Do you give the machine the same problem many times? Is that meaningful? And then the other thing, which I think is pretty novel that we tried out, was the use of confidence, self-reported confidence. So when you ask someone for an answer, you also want to say, are you confident about your answer? How confident are you? And that's something I feel, people have been, in the research world, we've been using LLMs to do these things for quite some time now. But I think the confidence question is quite novel from what we have done. So, going back to the final bullet point, what's the right way to do it, or what can we instruct a practitioner who might want to do this over the next few years? All right. So as I mentioned earlier, we had these 27 million press releases. Of course, we haven't done anything over all of them, but we ended up selecting just over about 1,000 headlines. So if you recall, we also used undergraduate subjects, and even, in a bigger picture, we were looking at relating the results from the students to the machine. But overall, it's this collection of about 1,000 headlines through which I'm going to give you some guidelines. And what we have done, so the A is accuracy and U is the number of unresolved tasks. So if you go back to the accuracy cost trade-off that I described, right? Obviously, as we chase more accuracy, there will be an execution cost that goes up, right? Maybe the better LLMs are more pricey, or other dimensions of cost. But NU is really relating to this, how many tasks get unresolved because you're chasing more accuracy. So the total cost function is going to combine both the cost of execution and this cost of dealing with the unresolved tasks in some other manner. And then the four things you see on the right side of the equation are the four dimensions, the configuration dimensions that I mentioned earlier, right? So our dependent variables are accuracy and cost, or unresolved tasks, and then the independent variables are those four dimensions. Okay, so what did we find with all of this? So let me take a minute on this picture. So you see four colors here. I'm sort of color not smart, but I think there's a red, green, blue. I'll call it blue and purple. And so that's the red and green are ChatGPT 3.5. And then the blue and purple are ChatGPT 4. And if you follow any color, of course, you see predictably an increase in accuracy or cost as you increase accuracy, right? So accuracy is on the x-axis and unresolved tasks or cost is on the y-axis. So that's straightforward. But the question is, among the different four variations that we have, the colors, what's the trade-off between accuracy and cost? And one thing you can see here is in our experiments that as you go to ChatGPT 4, which is the purple and the blue, you're able to achieve higher accuracy at lower cost of unresolved tasks. So of course, there may be a higher cost of using ChatGPT 4. That's not, so where you fall on an efficient frontier will depend on a practitioner's utility functions or the weights for different things, right? But what this is telling us here is this trade-off, but more importantly, as we looked, so I'll pass this. As we looked at the data more carefully, right, the question was this trade-off between accuracy and cost and the use of redundancy, right? As you ask ChatGPT, give ChatGPT the same problem multiple times, are you going to get the same answer? And what we discovered here that was really interesting is, one, asking a machine to do redundant work obviously increases cost, right? And our redundancy meant repeating anywhere from 1 to 25 times, right? So you're definitely increasing cost, and that cost would not increase accuracy unless you combined it in a particular way with self-reported confidence. So what you see here, I'm not sure if I can point. Which is this one? Okay. If you look at the label, the gray shaded region, that's redundancy at 100% self-reported confidence, meaning that a task is accepted as resolved only if ChatGPT returns the same answer every time with 100% confidence. And in that case, there is a gain in accuracy if there is an increase in cost. For the remaining cases, unless we use self-reported confidence, there is no gain in accuracy despite an higher cost, right? So that's an interesting insight from a practical point of view that do you want to use redundancy at all? Certainly do, because it increases accuracy, right? But if you do it in a sort of naive way without thinking of asking this LLM for confidence. And this was interesting because you might think, what does it mean for an LLM to report confidence, right? It was a tricky question in the beginning of our research project. And as we played around with that and tried these different levels of confidence, that's sort of the discovery we get from there. This next one is actually going, so by the way, this previous picture that I showed here is looking at those two dimensions of which version of the LLM and what kind of instructions do we give it, right? So all the dots are combining all the redundancy and confidence, right? So they're sort of telling you what's the trade-off on the version and instructions, assuming we're varying redundancy and confidence. So the next thing we did was to actually dive deeper into this issue of confidence and redundancy. And my eyes are not that good, so maybe I'll let Elizabeth talk about this picture because
can you hear me?
No, I'll give you this.
Okay. So the colored lines are the confidence threshold. So 0 is no confidence threshold, everything. And then we have the thresholds depend on the distribution. In this prompt, about 60% had 100 confidence, okay, which is why we have that be one of the thresholds. Okay, so it was a very skewed distribution, not true for all prompts, but for this one it was. So we have 0, 90, 85, 90, 95, and 100. And you can see that just applying a confidence threshold increases accuracy across redundancy. So just the confidence threshold alone will increase accuracy. But redundancy, which is on the x-axis from 0 to 25, at no confidence threshold, almost completely flat. Even at the 95% threshold, it's almost completely flat. And only at the 100% threshold do we get a relationship between more redundancy and higher accuracy. What redundancy means with confidence is that we average the confidence across questions. So if we just do redundancy in classification, which is it classified this way or not, we don't see a lot of variance, first of all, and we don't see an improvement.
All right. So I now have to wrap up here. So if you put everything together, right, what do we get? One, advanced LLMs and more detailed instructions obviously do better. But what's interesting here is in terms of an efficient frontier, they do better, if I can use that phrase, at less increase in cost than other ways of improving accuracy. And then as we just mentioned, redundancy alone without thinking of confidence doesn't really help. It would be a waste of time to ask the machine to repeat itself. And then this blend of redundancy and confidence is where we thought we got some meaningful insights. So at the end of the day, I mean, you can think of using an LLM for large-scale labeling as a way to break down a massive labeling project into 80% that can be resolved easily, and then maybe another 10, 20, 30% that requires more sophisticated methods to do the labeling. And so this is really isolating that 20 or 30%, right? And to summarize all this, I think we did something novel here in terms of asking the LLM to report confidence and playing with that to understand how confidence really mattered and this connection between redundancy and confidence. So I'm going to stop here because we are out of time, but we'll take questions.
We have probably just time for one question. And because we're recording, I'm going to turn the mic over and you get to be the question for tonight.
Just one question, no pressure. So the question I had was, another way to frame this could have been, I want to use cheaper models and then have an LLM as a judge, as an expert, which is a more expensive model. So did you consider reframing it that way to see what outcomes that would give?
We have talked about it. We haven't done it formally. So I think that totally makes sense to really scale up in that manner. Absolutely. Yeah, maybe there's one more.
We're really close.
Okay, now we can stop. Yeah.
Hemant, thank you. Very energetic and very interesting empirical finding. But how does one wrap one's head around the intuition of why reporting of self-confidence improve with repetition, like improves the results with repetition? What is the intuition behind it?
Do you want to address this? Because we've struggled with it. And until we look at this distinction between 100% and 95%, it did not make sense.
The intuition was our third co-author's innovation, so I don't fully have a sense of it. I think he wrote more about it in the paper, but I think neither of us have as much of an intuition. He was like, let's put in confidence. We're like, okay. And he had his reasoning, and it really worked.
All right. Thank you so much.
Thanks.